Did I switch it on? Can you hear me?
Yeah.
Good. So first of all, thanks to organizers, and thanks to all of you for coming to my talk. And once again, he's not here. I want to say congratulations to Adrian Matthias, but he's not here. Good.
He sent his apology.
Hmm?
He sent his apology.
Okay. So I will speak, as you can see, about Δ₁-definability of the non-stationary ideal on, and that's a joint work with Cy Friedman and Liu Zhenwu. So let me start with formulating the main result to which this talk is going to be devoted. So if kappa is a successor cardinal in L, then there exists GCH and cardinal forcing, cardinal preserving forcing, which makes the non-stationary ideal at kappa Δ₁-definable over H of kappa plus. Okay, and so here we have GCH, and we have a version of that exactly the same, just another poset which forces 2 to kappa to be kappa plus plus. Okay, you might think, why is that all interesting at all? Well, I don't know, but somehow there is this topic has been around for quite some time. So I think the first result in this direction is due to Meckler and Van Anen from 1993. They proved that consistently the non-stationary ideal at omega 1 can be Δ₁-definable over H omega 2, and also GCH holds in their model. And how does the proof go? The proof goes as follows. They proved that the statement of the theorem is equivalent to the existence of a certain tree, which they call omega 1 canary tree. And omega 1 canary tree, it's a tree which has height omega 2. Let me say better, what is kappa canary tree? If kappa is a regular cardinal, kappa canary tree, it's a tree of height kappa plus, size 2 to kappa, which has no cofinal branches. But whenever you kill stationarity of any stationary subset of sets of cofinality kappa below kappa plus, then in such a forcing extension, this tree immediately gets a cofinal branch. So the existence of such a tree, as I said, is equivalent to Δ₁-definability of the non-stationary ideal at omega 1. And the existence of such a tree was established again in 1993 by Meckler and Schellach. But as it's often the case, papers by Schellach are kind of globally correct, but locally hard to understand. And the proof had to be repaired, which was done by Hyttinen and Rautila in 2001, who in general forced a kappa canary tree for any regular kappa by GCH and cardinal preserving poset. Okay, so if we combine everything which I said, we get the following result. So let kappa be a regular cardinal. So the existence of a gamma canary tree implies, in fact, is equivalent to the Δ₁-definability of the non-stationary ideal on gamma plus restricted to set of points of cofinality gamma. That's as gamma plus gamma. And assuming GCH, we can produce a gamma canary tree by GCH and cardinal preserving poset. Okay, that's another results along this line due to Friedman, Hyttinen, and Kulikov. They're a bit more recent, and they showed that if kappa is equal to kappa to less than power kappa and is regular cardinal, which is not a successor of singular, then you can, then they kind of produce a what? Okay. Then they produce a GCH and cardinal preserving poset, which forces the non-stationary ideal at kappa restricted to S to be Δ₁-definable. And it was very essential in their proof, and I will say it later, to make S to assume that S is co-stationary. You might ask, I mean, why isn't it not important that S itself is stationary? Well, if it's not, then the ideal restricted to it is just the power set of S. It's trivially Δ₁-definable over H of kappa plus. And another result is that if you have a measurable kappa, you can and you fix some normal measure on it, then you can force the non-stationary ideal restricted to a given measure zero set to be Δ₁-definable, and you can preserve measurability of kappa. And in fact, you can also prove that by similar ideas that non-stationary ideal at omega 1 is Δ₁-definable and precipitous, assuming one measurable, you can force that. Good. And just before you prove that anything is consistent, it's kind of in general know that this is not true in ZFC at all, that we have to work a bit. So there are also negative results, and the first one is due to Friedman, Hutinen, and Kulikov, who proved that if kappa is uncountable and equal kappa to the power less than kappa, then the non-stationary ideal restricted to a set of points of cofinality lambda for a given regular cardinal lambda less than kappa is not Δ₁-definable in the model obtained after adding kappa plus many Cohen subsets of kappa. And also if V equals L, no restriction of the non-stationary ideal is Δ₁-definable. So at least that's what we would like to force is not true in ZFC. And if kappa is weakly compact, then the non-stationary ideal at kappa is not Δ₁-definable over H of kappa plus. Okay, so there are negative results and some applications. So now it's, as you could see during this week, there are more and more people who are kind of interested in generalizing the classical descriptive theory results at the level of omega to higher levels, to some larger cardinals. And the typical setting there is that you consider some regular cardinal kappa. Typical assumption is kappa is equal to the kappa to the power less than kappa, and consider this product with the less than kappa box topology, which means that basic open set in the topology is obtained as follows. You take some partial function with domain of size less than kappa, and the basic open set given by that function is just everything which extends it. Okay, and if you just replace in the definition of Meagher omega with kappa, you get the notion of a Meagher subset of kappa to the power kappa. It's just the union of kappa many lower than subsets. And the Bayer property is defined exactly as in the omega case. And one of the main differences, which makes it quite kind of look not that much similar to the case kappa equals omega, is the fact that you have sigma 1 definable subsets of kappa to the power kappa, which do not have the Bayer property, whereas at the level of omega, this is one of the classical results, probably by now 100 years old, that this is actually every analytic subset of reals has the Bayer property. So that's why the non-stationary ideal is a kind of a useful test space for this higher level descriptive set theory. And okay, so our result says that actually, since we know how to make it Δ₁-definable, even Δ₁-definable sets do not have to have the Bayer property in this uncountable setting, but even the analogy fails even worse. Namely, there is another classical result by Hoda and Schellach from '89, who showed that all Δ₁-2 subsets of reals have the Bayer property is equivalent to the statement that for any real there is a Cohen real over L for any real x there is a Cohen real over L of x. And just as you can see from in the proof, I guess I will come to that later. In our case, we are exactly in this situation, namely for any subset of kappa, we have another subset of kappa which is Cohen kappa generic over L of x. That just holds in our model, but nonetheless the Δ₁-definable set, the non-stationary ideal, is not does not have the Bayer property. So even Cohen reals, unlike in the case of omega, do not help to get the Bayer property in this generalized setting. Good. And let me just give some basic ideas of how does the proof go. So we prove it for for a successor cardinal. So kappa is gamma plus in our case. The first part, we just get the part with GCH because the other part is just tiny modification of it. And the key notion for the proof is a notion of a suitable model. It's just a model of a portion of the F which contains gamma plus 1 and in which you can compute gamma plus plus. And moreover, it agrees about gamma plus plus with its version of L. So that's a suitable model. And of course, if it agrees about gamma plus plus with its version of L, then it must agree about gamma plus. Okay, now maybe I have to paint something. Oh. Sorry about that. Let me come back a couple of slides to this result of Friedman, Hyttinen, and Kulikov. So why was it important here to assume that S is co-stationary? Well, stationary subsets of the complement of S were used for coding the Δ₁ definition of the non-stationary ideal on S. How? You just carefully, you just take a bunch of these stationary subsets and then you kill stationarity of one of them, preserving stationarity of others. And this is used just to code the fact that on S you have this Δ₁ definition. But this method is not anymore available if you would like to code the Δ₁, the fact that the whole non-stationary ideal is Δ₁ definable, because it's kind of funny to kill stationarity, because if you kill stationarity, then maybe later it may happen that you already produced the witness for Δ₁ definition for it, and then later you killed the stationarity, and this would kill all the machinery. So in general, to avoid this, that would be very kind of messy. That's why in our proof we also use stationary kill for coding, but one level higher. Okay, so we fix a nice sequence of length kappa plus of mutually disjoint stationary nice means definable, because later on we will need to know that any suitable model has its own version of this sequence. It just applies the same definition to compute it, and they should be mutually disjoint, live on sets of cofinality kappa, and their union must have stationary complement. This is just for technical reasons. And how do you get it? You just take some nice diamond sequence and just look at the places where it guesses singletons, and that's how you get this stationary sequence. And now I think I'm able to present the Δ₁ definition, but even though in the formulation I always speak about non-stationary ideal, for technical reasons we will just produce Δ₁ definition of the collection of all stationary subsets of kappa. So, well, the pi1 definition is obvious, right? The set is stationary if for every set C, if C is a club, then it has an empty intersection. So we already, pi1 is kind of clear. What is interesting is how to produce a sigma1 definition for the collection of all stationary sets, and that's here marked in red. So at the end, in our forcing extension, we will have the following sigma1 definition. S is stationary if there is a witness for it, that's my Y, such that any suitable model M of size gamma containing Y up to its gamma plus, well, there is some place such that the block of I'll just paint it in a while, the block of stationary sets from this collection as alpha is arranged the way I want it. So I think at this point it would be nice to paint something. So you have this sequence vector. Again, for technical reasons, rho, I define rho to be kappa plus 3. And now I just divide this sequence into blocks of length rho. So the block number alpha will start with alpha times rho, and will end with alpha times rho plus 1, which is, yeah.
All times alpha.
Yeah, exactly. So alpha times rho plus.
All times alpha.
Oh, yes, sure, yeah. Times alpha plus 1 plus kappa plus 3. So that's already is going to be the first ordinal from the next block. So I'll better write here -1. Okay. So how the stationary subsets of kappa will be coded? Of course, there will be some bookkeeping function f, and you arrive at your block number alpha. So you, of course, it's going to be some iteration. So you are at stage alpha times rho of your iteration. You look at the next block, and you turn your set S into the set which I denote by T of S. You see, if you know T of S, you can uniquely determine S and vice versa. But why T of S is better for technical purposes, the point is, of course, that if T of S0 is a subset of T of S1, or vice versa, then it implies that S0 equals S1. So you don't really have to know that you have one-to-one match. It's just being a subset is okay. Now, here, from this stage to this stage of iteration, you kill stationarity of those S with index alpha times rho plus zeta, such that zeta is in T of S. So we kill the stationarity, and just by genericity, all others will remain stationary. And now, like the first stage of kind of the first level of this delta-1 definition is already clear. You say that at the end, you will say that your set S is stationary if there exists some alpha such that for any ordinal zeta, stationarity of S of alpha times rho plus zeta is killed if and only if zeta is in T of S. Okay, but that's not quite what we want, because remember that these are stationary subsets of kappa plus. So you just use, it's not a definition over H of kappa plus, it's a definition, I guess, over H of kappa double plus. So we have to, what? It's not that bad, because we're actually coding stationary subsets of kappa, and we are killing stationarity one level up. So that's killing stationarity is not that horrible. I mean, the bad thing is that it's not.
The definition uses stationary. The definition for stationary kappa uses stationary kappa plus.
Yes. But as you see, the version, the mth version of it, of some.
M.
Exactly. So what I said is just the first approximation of the definition. Now what we have to do, we have to turn it into a real definition over H of kappa plus. So we have to kind of reflect this situation down. So how do we do it? Oh, that's just, of course, when we say that M satisfies something, then we mean the mth version of all these stationary sets. So how do we kind of make this all happen in all small suitable models? So that's to pull this situation down, we will use almost disjoint coding. So we need another sequence of, now we cannot guarantee that they are disjoint, but almost disjoint subsets of kappa, which live on cofinality gamma. And again, you can get them from the diamond sequence. And we need this bookkeeping function, and we define an iteration. Okay, so we already know what happens from alpha times rho to alpha times rho to kappa. Right? We just kill stationarity depending on whether an ordinal appears in T of S or not. Now, how do we copy, kind of reflect these facts down? Well, by induction, we define our poset big C. We assume that we are done. Look, write it in the form rho times alpha plus zeta. And well, if f of alpha, the bookkeeping function, gives some nonsense, we just reply on that with a trivial poset. So assume that it gives us a name of a subset of kappa, which is forced to be stationary. And 4 cases are possible. Again, let me remind you what is T of A. So the first case, I guess I already described on the blackboard. It's the case when this zeta is less than kappa. So here you just kill, depending on where zeta lives, you kill with the most obvious forcing which you have, just bounded closed sets which are disjoint from this stationary set. You kill the stationarity whenever you want, whenever the index appears in T of S. In this case, S is just what my bookkeeping function gives me, f of alpha, evaluated by the generic G. Okay. More interesting cases are what we do at stages kappa plus 1, and the kind of the punchline of all that is kappa plus 2. So here I need some definitions. If you have a set of ordinals, odd and even has the obvious meaning, just odd and even, and I just denote by the alpha some subset of kappa plus, which codes. Along the construction we will get a sequence of names, these y betas, which will be actually a witness. If you remember my red definition, there exists y, so these y's will be witnesses for the Δ₁ definition. So that I already have them up to alpha, and so the alpha subset of kappa plus just codes the sequence of these witnesses and the sequence of the clubs which we have shot thus far. And you know, just that you don't think that the word code means something deep here, I wrote these 4 lines, but just don't read them. This is just to give you an impression that this is very easy, what I mean by code. Okay, and now at this case, QXC, remember that Xc is just the next one. It's the forcing which we do at the stage alpha rho plus kappa. So that's almost disjoint forcing which codes the alpha into a subset of kappa using the sequence. We have, remember, another sequence, but this time of subsets of kappa. This is A alpha less than kappa plus. They're mutually almost disjoint, and we will use them to code the alpha into a subset of kappa using the almost disjoint coding. How does it look like? I guess I don't really have to give you the definition, because alternative name for the almost disjoint coding is just Mathias forcing for the filter which you get if you pass 2 complements of the sets of A alpha. Look at the filter which they generate, but take only those A alphas. Well, alpha is of course a bad choice here. Take only those AIs such that I appears in G alpha. So then if you look at the complements, take the filter, generate force with Mathias forcing, then at the end what you will get a generic set which I denote by x0 alpha, and it will have the property that the alpha will be exactly those elements in kappa plus, new in kappa plus, such that x0 alpha is almost disjoint from A nu. Okay, so just use almost disjoint coding to produce a copy of this, not a copy, but kind of a relative of this, the alpha coding everything which happened thus far to kappa. Good. And the next step, so case 3. So what do we do next with this x0 alpha? So yeah, maybe I should lost the only piece of, oh yeah, they have some different color. So here we have some d alpha. It codes everything which happened thus far. So this d alpha, using these AIs, we have here already a subset x0 alpha. Now we take a strictly increasing continuous sequence of elementary submodels of L theta. Theta is some just large, not large in the sense of measurable, just big cardinal, and look at L theta of x0 alpha, and we fix as continuous strictly increasing sequence of elementary submodels of it, which contain kappa and x0 alpha. Of course, we look at those which have cardinal of size kappa, and so E alpha will be the club in kappa plus, which consists of versions of kappa plus of the Mostovsky collapses of these models. Okay. So here we have another.
Please use the white chalk.
Oh yes, I just couldn't find it. I didn't know that it's here. Okay. So we have kappa plus, kappa, and you have a club which consists of kappa plus of elementary of collapses, of Mostovsky collapses of elementary submodels of size kappa of some L theta of x0 alpha. So this will be a typical element of this club. So why do we actually doing this? Maybe a couple of more lines. So we take another set Z alpha, which inside incorporates both this D alpha. Remember, D alpha was just a subset of kappa plus, which knows all the story what happened thus far, all our generics and etc. And that's on one part of it. On the other part, we just what we do, we arrange it that whenever you have a suitable model M, which contains this Z alpha up to its version of kappa plus, then the version of M of kappa plus must be in the club E alpha. Okay, and that's easily done by placing in the alpha a code for bijection with kappa, if you just move slightly more. So what's the idea? You see, if you want to have some definition which involves suitable models of size gamma, just by elementarity, there is no way to avoid forcing, not in the sense of forcing, but just, we have to make that the same thing holds for all suitable models at higher levels. Okay, and we know actually that what we want, because we already made stationary kill. What we want, it happens in L theta of x0 alpha, because x0 alpha codes the D alpha, and the alpha has all our previous generics. So once you are in L and you have x0 alpha, you know actually which stationary sets in this block number alpha we have killed. So the whole universe has the correct picture of where the stationary kill happened, where not. Now we want all all suitable models of this kind, which of size kappa, also have this correct picture, but a part of these suitable models, which are actually Mostovsky collapses of elementary submodels, will have by elementarity this correct picture where the stationary kill takes place, where not. But there are obviously suitable models which are not Mostovsky collapses, and you have to take care of them. So how do you do it? You arrange for them a helper, which first of all makes their version of kappa plus to land into the club, which consists of versions of kappa plus of collapses of elementary submodels. So at least what we arrange is that whenever we have some suitable model M, which contains what was my notation, Z alpha, which contains Z alpha up to its version of kappa plus, then it has the same kappa plus as one of the collapses of elementary submodels. So notice then it has kappa plus is gamma plus plus of M, okay, and it equals gamma plus plus of one of these N collapses of N nu. So M then agrees with one of these collapses of elementary submodels on gamma, obviously on gamma plus, which is kappa because it contains kappa, and on gamma plus plus, which is already good. They at least become a bit coherent, which makes our chances better. Okay, so now we have this Z alpha, but again it leaves too high. We would like to to have its relative down in kappa. So we do the same trick. We use the same sequence to code it down via almost disjoint coding, or if you wish, Matthias forcing for this meeting for appropriate filter, and we produce a subset of kappa x1 alpha, which allows us to reconstruct this z alpha. Namely, z alpha is the set of all those new in kappa plus, such that a new elements of our almost disjoint collection of subsets of kappa has bounded intersection with in x1 alpha. Good. So as a result, we have the following thing, that if M is any suitable model which has kappa, contains kappa as a subset, and these two guys, x0 alpha and x1 alpha, of size kappa, size kappa, it just follows from the fact that it has gamma plus plus smaller than actual gamma plus plus, then it satisfies the following formula, where formula says that using sequence a vector, the set x, which in our case will be x0 alpha, it almost disjointly codes another subset of gamma plus plus, which was kappa plus in our case, which knows everything what happened thus far. That's our d alpha, which knows all y's, these witnesses, and knows all stationary queues in block number alpha. Okay, why does this happen? This happens actually for the following reasons. First of all, since x1 alpha is in our model via almost disjoint coding can decode the z alpha. So since it contains x1 alpha, so therefore the sequence a vector is nicely definable. So therefore it contains z alpha intersected with gamma plus plus of M, which is kappa plus in M. Okay, and since it contains the alpha up to here, it agrees with the Mostovsky collapse of some elementary submodel on gamma plus and on gamma plus plus. And notice, therefore, they both have their own versions of L, which agree on gamma plus and gamma plus plus. And there is a remark that all our coding machinery is a kind of very much L, kind of close to L. So whenever you have two suitable models which agree on gamma plus and gamma plus plus, then if one of them satisfies this formula psi for some parameters, then this happens if and only if another satisfies. So that's why actually M satisfies formula psi, because by elementarity corresponding collapse of an elementary submodel does satisfy it, and therefore by a remark you have the same in M. Good. So we somehow took care of suitable models, which are not yet the suitable models we wish. They are still too high. That are suitable models which have correct version of gamma plus, namely which contain kappa. And so the most interesting part of the forcing is the localization forcing, which we do at the very last stage of this block. That's stage alpha times rho plus kappa plus 2. What does it do, this forcing? It localizes this property which I described before down to suitable models of size gamma. And it was, I guess, the trick was invented by René David, but since then I guess it has been hundreds of times used by Cy Friedman and his collaborators. So the poset consists of all functions from some ordinal below kappa into 2, and just divide the domain into 3 obvious pieces. On one piece we code x0 alpha, one of our helpers. On another piece we code x1 alpha, and the third piece is actually the working one. And you demand that if whenever you have a suitable model of size gamma which contains the restriction of this R to its gamma plus, then M satisfies the formula which I described on the previous, which I have written on the previous slide. Basically, the formula is, it's impossible, of course, to remember what's that, but it's just a very wordy and precise reformulation of the red characterization of stationary sets which I presented at the very beginning. Okay, the order relation is given by extension, and it produces a generic function from kappa to 2, which is characteristic function of the subset Y alpha, and that will be our witness for stationarity, for the sigma 1 definition of the stationarity of the set S, which we take care of at this stage alpha. Okay, so that's forcing, but support. You see, we are doing things at different levels. We are doing this stationary key at level of kappa plus, and then we are doing Mathias forcing for filters on kappa, and then we are doing some other kind of funny forcing due to this localization forcing. So the support is like to let everybody be happy. So the forcing which live on size which you do at level kappa plus, they have supports of size less than kappa plus, and it's mixed support iteration. And on other coordinates, we so where we have these functions of localization forcing and almost disjoint coding, that's going to be a support of size less than kappa. Okay, so this is just formally described what's that. And yeah, so the poset the delta consists of those functions with domain delta, such that at most kappa many coordinates where we kill stationarity are non-trivial, and fewer than kappa many coordinates where we do localization almost disjoint coding are non-trivial. Everywhere else it's forced to be trivial. Good. So we complete the definition, and that's one of the occasions this proof when to kind of compose the correct forcing is more difficult than to prove that it does what you want. So actually, but nevertheless, I will say a couple of words. What kind of steps in the proof should be done? First of all, it's very crucial for us to prove that it's the poset is less than kappa distributive. Why? Imagine that that it's not. So at stage alpha, you produced your nice definition for the stationarity of S, which you've got by your bookkeeping function, and then suddenly later on you have objects of size gamma, of size less than kappa. So this kind of produces for you more suitable models of size gamma, and how to take care of them. You know, they will kind of appear cofinally often, and okay, maybe you can just take care of S cofinally often, but then you have not just one witness, you will have kappa plus many witnesses, which kind of kills all the arguments. So that's crucial to prove that P is less than kappa distributive, that you don't produce any objects of size less than kappa. And how does the proof go? The main idea is just to be a bit bold and to prove that you have a dense subset of your forcing which look as simple as possible. Namely, whenever a coordinate is involved where you do either almost disjoint forcing or localization, these coordinates where the poset have size, where we use support of size less than kappa, that you have a checked name. So then, just by induction, you prove that indeed the collection of all these conditions is dense in your poset, and yeah, that's crucial for the proof that of the distributivity. Well, another thing is just guess. Okay, so let me remind another definition. So if you have a poset and you have some condition, then Q, everything is in some model N, then we say that Q is strongly NQ generic if Q is an element of every open dense subset of the poset, which is an element of N. So now again, we have some large enough regular cardinal theta and some N, and we construct just by induction an increasing continuous chain of sigma 1 elementary submodels of L theta, which starting with some set N, some set X, and we do it in a minimal way. So we always take at limit stages we take unions, and at successor stages we just close the singleton and xi with respect to all scaling functions, sigma 1 scaling functions. And such a sequence will be, we will call it minimal sequence generated by x. So the key idea to prove the distributivity is to prove by induction on xi less than kappa plus is just to show that this set of nice conditions where everything is checked whenever you speak about objects of size less than kappa, that it's first of all dense, and you have this statement dagger theta, which says that you can produce many strongly generic conditions. So you see already dagger theta implies the less than kappa distributivity, because if you take your x to be a collection of gamma many open dense sets, then already the fact that stronger condition q prime is n0 peak c generic says that it must land into intersection of all of them. It was slightly too technical, I guess, but what is important from here is the use of the sequence of elementary submodels, because they will come up later. Well, another thing which is important is to show that we do not mess up with stationary subsets of kappa. Well, why is that? Imagine that, again, you arrived, we know already that we are less than kappa distributive. You arrived at stage alpha, you've got your stationary set S, and you coded, you produced a witness for sigma 1 definition of it. And now imagine that at some later stage, you killed its stationarity. But notice that the sigma 1 definition of it persists, because it refers to suitable models of size gamma. We do not produce any new objects of size gamma, so the definition will stay until the end, but you killed the set for which you have a witness. So we've got a witness for set which is not anymore stationary. That's why it was kind of essential to see that if a set was at some point forced to be stationary, then it will remain stationary until the end. And here we used square kappa sequences, square gamma sequences for what? Namely, at some point, you have to deal with some suitable model, and you don't know what to do with it. So you'd better rule it out. How do you rule it out? You produce in what you think it is its version of gamma plus a sequence of length gamma, cofinal in it, that this M knows it, right? So typically, we produce it either from kappa plus versions of collapses of these elementary submodels, of which we have a chain of length kappa, or that was in the previous case, because it was always sequences of length less or equal than gamma. But here we have to obviously deal with sequences of length above gamma, and then you need square just to be able to rule out suitable models which you don't want. And another thing is, of course, we also have to take care of preservation of stationary subsets of kappa plus, namely those which we didn't kill intentionally. Because imagine that if at some point, well, we have some coding, we killed some on purpose, stationary subsets, but suppose that just by chance, by bad luck, we killed one of those which we didn't mean, then of course in the universe, this fact will be known, right? And then the elementary submodels of size gamma will kind of grasp it, and then their collapses will give you a wrong picture. So it will kill all the coding machinery. So another key step is to see that stationary subsets of kappa plus, which were not supposed to be killed, are actually not killed. This is some ideas of the proof which I will skip. And well, you see, since our forcing has kind of different levels and very unclear, I mean, it's clear that it's kappa, I guess, double plus cc. Anyway, I mean, there is no good counting on names available a priori, right? We cannot really, we don't know, so we would like to iterate until kappa plus, but until now it was unclear why actually we could set up bookkeeping which will hand us all possible names of subsets of kappa, about which we have to decide is it stationary or not. And actually, it's true that for any name of a subset of kappa, that was actually the proof can be devised from the proof of the preservation of stationary subsets at kappa plus. That it has a name of size kappa, and only now at the very end of the proof we can happily state that the bookkeeping is actually possible, and so we have appropriate bookkeeping, and yeah, that's basically all of it. Thank you for your attention.
Any questions or comments? So you start out with L because you want to code these nice subsets. Are there any, for example, large cardinals that you know that you cannot do this over? That there's no forcing that will do this for this kappa, no nice forcing.
Well, I think I guess I mentioned it, that the non-stationary ideal at weakly compact is not Δ₁-definable over H of kappa plus. So
I see.
if you kappa,
keep it weakly compact, it will not be.
yes, so, and weakly compact, they survive into L, so it was kind of essential for us. So we strongly use the fact that kappa is actually successor, and
no, maybe I think I didn't formulate my question. So, is there a universe which is so far away from L that you know there is no such theorem?
No, I don't know. I mean, okay. No means I don't know. Not that.
That's your answer. Okay, thank you.
Yeah.
Any other questions? No? Okay, let's thank Lyubomyr once more.